All right, so we are going to look at the same problem we did in the previous video. We are using Riemann sums to approximate the definite interval from 1 to 3 of x squared minus 2 dx using the left-hand rule. And now we are going to do n rectangles instead of 10 rectangles. So we are going to mirror what we did using n rectangles instead of 10. So this time around, we still have a total width of 3 minus 1, or 2. Right? From the beginning of our integral to the end, we went from 1 to 3. We have a total width of 2. We are going to split that 2 over n into rectangles. And so we have 2 over n, which cannot be simplified since we don't know n at this point. So our first rectangle would be from x equals 1 to 1 plus 2 over n. Our height would be f of 1 in this case, because that is the left side. So again, it's just 1 squared minus 2, or negative 1. And then our area would be our width of 2 over n times our height of negative 1, and we get negative 2 over n. So that's our first rectangle. We really care just about the ith rectangle, the general formula. So for our ith rectangle, we're going to go from x equals. Now the first one was at 1, and then for each additional rectangle, we should move over by 0.2. We're going to add on I minus 1 times 0, sorry, not 0.2. We're going to add on our width of 2 over n. So times 2 over n. So again, that first rectangle, we don't want to add any width or any shift at all. So that's why we did I minus 1. So we didn't have a shift. And then we'll go to 1 further. So we'll have x equals 1 plus I times 2 over n. Our width is still 2 over n. And our height will be f of 1 plus I minus 1 times 2 over n. And so we have 1 plus I minus 1 times 2 over n. That whole thing squared, and then minus 2. So this is the height of the ith rectangle. For the area, we will do width times height. So 2 over n times 1 plus I minus 1 times 2 over n squared minus 2. Now we know the ith rectangle. We are doing n rectangles. We can go ahead and just sum up those n areas. So we have then that the definite integral from 1 to 3 of x squared minus 2 dx is approximately, we will do the sum from I equals 1 to n of 2 over n times 1 plus I minus 1 times 2 over n. That whole thing squared, and then minus 2 and n brackets. Then we could go about evaluating this. So that 2 over n we can pull out front. We have 2 over n times the sum from I equals 1 to n of If we expanded this out, we would have 1 plus 4 over n times I minus 1 plus 4 over n squared times I minus 1 squared minus 2. Continuing to expand, we have 2 over n times the sum from I equals 1 to n of, let's see, the 1 minus 2 becomes negative 1. Then we have plus 4 over ni minus 4 over n. And then this last part would become plus 4 over n squared times I squared minus 2I times that, so minus 8 over n squared times I, and then plus 4 over n squared. And so we can simplify further. This becomes 2 over n times the sum from I equals 1 to n of, we will have a negative 1 minus 4 over n plus 4 over n squared. So I'm just going to put that together. Negative 1 minus 4 over n plus 4 over n squared. And then in multiplying I, we have plus 4 over n minus 8 over n squared times I. And then we have plus 4 over n squared I squared. So from here, we can then go ahead and evaluate our sums. So we have a 2 over n out front. That first sum, we will have n times negative 1 minus 4 over n plus 4 over n squared. Then we will have plus, we will have I is n times n plus 1 over 2, and then times 4 over n minus 8 over n squared. And then plus for I squared, we have n times n plus 1 times 2n plus 1 all over n squared, all over 6. And then that is multiplying 4 over n squared. So this is kind of the nasty version of the formula that we could evaluate plugging in n. Just a side note, when we do have the I minus 1s involved, we could do a shift. So with the I minus 1s involved, if you wanted to, instead of actually multiplying out the I minus 1s and I minus 1 squareds, we could just do a little simplification and essentially run from I equals 0 to I equals, or to n minus 1. And then you could just plug in when I equals 0 what you get. Or sorry, we could shift this. If we change it to j, set j equal to I minus 1, we would basically be running from j equals 0 to n minus 1. And then you could figure out what the first term would be and then look at it running from 1 to n minus 1. That uses a little less algebra. I apologize, that was just a messy explanation. But we can use our algebra and run it out. The nice thing about using Riemann sums ultimately for approximate definite integrals is ultimately it's not going to matter which one we use, and the right-hand sum is much more pleasant and doesn't require any shifting. And so we will mainly use the right-hand sum. Your homework, you will have one left-hand sum, but then we will switch to using right-hand sums. And it'll be a little more pleasant because we will not have I-1s involved. All right, so that is figuring out for n rectangles. And then from here, let's just go ahead and kind of summarize what our general formula would be. So the general formula for the Riemann sum to approximate the definite integral from a to b of f of x dx with the left-hand rule and n rectangles. Our width of one rectangle would just be b minus a divided by n, split the total width over n rectangles. Our rectangles, so this is for the ith rectangle. The rectangle would go from x equals a plus I minus 1 times this b minus a over n to x equals a plus I times b minus a over n. The height would be f of this a plus I minus 1 times b minus a over n. And so we would do the definite integral from a to b of f of x dx is approximately the sum from I equals 1 to n, our n rectangles, of our width, b minus a over n, times our height, f of a plus I minus 1 times b minus a over n. And then that b minus a over n is a constant, and so we can go ahead and shift b minus a over n outside. And then we just have the sum from I equals 1 to n of f of a plus I minus 1 times b minus a all over n. So again, we did 3 minus 1 was our b minus a. We split that over n rectangles. That was that 2 over n that kept popping up. Otherwise, this should look essentially like what we were doing in the previous problem. So for the next 2 videos, I'm not going to use a specific number like we did for 10 rectangles in the prior video. We will just look at the right-hand rule and midpoint rule using n rectangles.